So it's my pleasure to welcome the next speaker, Priya Donti, who's from Carnegie Mellon University. He's going to be talking about inverse optimal power flow, assessing the vulnerability of power grid data. Priya is a third-year Ph.D. student in the Computer Science Department and Department of Engineering and Public Policy at CMU. Her research is in the intersection of deep learning and energy policy, exploring topics such as marginal emissions prediction, grid data vulnerability, and end-to-end task-based approaches for coordinating between grid forecasting and control. Thank you.
Okay, yeah, thanks so much for having me here. So my name is Priya Donti, and I'll be talking about some work that's joint with my advisors at CMU, Inês, Azevedo, and Zico, Kolter, on assessing the vulnerability of data on the power grid. So there is a lot of public data on the US power system, and I would argue that it's for very good reasons. So grid operators, for example, publish energy prices on a relatively granular scale in order to promote market transparency. And the US Environmental Protection Agency also publishes how much electricity large fossil generators are producing at each hour in order to do emissions monitoring. So I would argue that there's a lot of data out there for very good reasons. On the other hand, there is also a lot of power grid data that we would like to keep private. So for example, electricity generators in some parts of the US bid into a market in order to compete to produce electricity. And if one electricity generator were to know another electricity generator's costs, they could game their bids in order to try to produce more electricity. And this could drive prices up for consumers. So as a result, we'd like to keep generators' bidding costs hidden in order to promote market efficiency and fairness. As another example, we would like to keep things about the grid's structure hidden. In particular, if an adversary were to know certain aspects of the power grid structure, they could potentially hack the grid or make it collapse. And so this is potentially a cybersecurity concern. And so as a result, grid operators have invested a lot of time in trying to figure out how exactly to either keep data private or to react to the exposure of data that they would like to otherwise not have be public. And there have been a lot of prior approaches to this. So in markets, in electricity markets, there's a combination of retroactive approaches and proactive approaches. So retroactive approaches ask the question, can I look at how my market operated in the past and see if it was actually operating efficiently and fairly? And then proactive approaches include mechanism design. So can we actually design markets that are going to operate efficiently and fairly, given what we know about the actual system? On the cybersecurity side, some folks would do threat modeling. So asking questions like who or what can threaten the power system and how exactly would that happen? As an input to both of these kinds of analyses, one would need to do a data vulnerability assessment. So ask the question, can we understand what information on the power system is actually at risk? And then use that information to actually do our cybersecurity assessments and our market efficiency assessments. And so the work that we present here is kind of in this third camp. We're trying to assess the vulnerability of data on the system. And so specifically, the question we're asking in this work is whether private power grid information can be reverse engineered from public power grid information. So specifically, as I mentioned earlier, in the US, we tend to know how much power electricity generators are putting into the system at a given time. And we also tend to know the energy prices at various places on the system. What we don't want to know, or we don't want released, is the actual costs at which electricity generators are bidding into the system. And we also don't want released the grid structure. However, we do know how the public and private quantities are related to each other. They're related through a problem called AC optimal power flow, and this is basically the mechanism through which grid operators schedule electricity generation in order to minimize the system costs. And so the way we formulate our reverse engineering problem, the ability to reverse engineer private data from public, is through something we are calling inverse optimal power flow. Essentially, can we find the inputs to the ACOPF problem, to the AC optimal power flow problem, that produce public outputs that look like the data that we actually observe on the system? So basically, if we estimate generator costs and grid structure, do we actually get power generation and electricity prices that match the power generation and electricity prices that we see in the real world? So the way we solve this inverse optimal power flow problem is through gradient descent, a pretty standard method. And here's the pseudocode for that algorithm. At a high level, what the pseudocode is saying is that we start with a bunch of public data and also some initial guesses for what we think that the private parameters, what we think the costs and grid structure should be. We then, going through this, basically we take our guesses, we put it through the AC optimal power flow algorithm, and we get some estimates for what we think the public quantities should be. And we compute the loss between, or the error between, the public quantities that we estimate and the public quantities that we actually see. And then we use the information about that error to update our estimates for what we think the private data is. So essentially, while there is some gap between what our algorithm thinks the public data should be and what the public data actually is, we iteratively use the gradient of this error to update our parameters. And when our outputs match the real public data, we stop. So in principle, this algorithm looks actually relatively simple. But there's something tricky about it that I haven't told you yet. And that is, exactly what does this AC optimal power flow problem look like? And in particular, AC optimal power flow is actually an optimization problem. So the formulation is here on the slide. And in particular, grid operators will try to minimize electricity costs. That's the objective of the problem, subject to some linear inequality and equality constraints that we might have on the system, as well as one constraint that we call the power flow constraint that basically describes the physical attributes of the power grid. To relate this to the inverse problem that I show above, this variable z that power operators are optimizing over is what contains the power generation. And for those who this means anything to, the dual variables on that power flow constraint are actually what our electricity prices are. But for those who may not know what that means, basically the AC optimal power flow formulation is what is giving us our estimates of power generation and electricity prices. And the tricky part about this is that now what you see on the screen in front of you is an optimization problem embedded within an optimization problem. And this is actually what we're trying to somehow take gradients through. And so to go back to our stochastic gradient descent, or a gradient descent algorithm here, to compute that particular gradient that's highlighted in the red box, to compute the gradient that we need to update our public parameter guesses, we need to compute something like this. So in particular, for each parameter we're trying to guess, we have to compute the gradient of the loss with respect to that parameter. And if you run out the chain rule, you'll get something that looks like this. And in particular, the thing I'd like to highlight is that taking this gradient involves taking gradients through the outputs of the ACOPF optimization problem. So we have to know what the gradient of the power generation is with respect to our parameters and what the power prices is with respect to our parameters. So the way we actually do this, the way we actually differentiate through the AC optimal power flow problem, I'll talk about this at a high level, but you're welcome to ask me details after. The first step is that we formulate this optimization problem as a quadratic program, or actually a sequence of quadratic programs that we solve. And then at the end, when we've actually solved the problem, we write out what are called the KKT conditions of that problem, so the conditions that are necessary and sufficient to describe the optimal conditions of that problem. We take derivatives through those KKT conditions and use that to write out a linear system we can use to solve for the gradients, and that linear system is what you see on this slide. In practice, we're actually able to really efficiently compute these gradients using backpropagation in a neural network. So to recap, and if those last two slides didn't make sense to you, don't worry too much about it. The main idea here is that essentially we are able to reverse engineer, to some extent, the AC optimal power flow problem that power operators use to schedule electricity. And by doing that, we can try to extract some of the private information on the power grid from public information. So in theory, this is all well and good, but does this actually work? And so at the moment, we've started to test this out on a couple of power system test cases with a plan to expand to testing on larger systems later on. And so on the next few slides, I'll show you our preliminary results for a 14-node test case, where we assume we have 200 points of public data. And in these experiments, instead of assuming that we don't know anything about the system and then trying to learn everything, we kind of started by saying, imagine we only don't know some part of the data, can we recover it? So in our first set of experiments, we assume we know everything about the structure of the power grid, but that we don't know anything about the costs that the electricity generators are bidding into the market. So on the graph shown here, what we have is the results for 3 different electricity generators on the system. And on the y-axis is the squared error of our estimate for 2 different cost parameters for each generator. On the x-axis, what you see is that we ran multiple experiments. We ran one set of experiments in which we assumed we only had one piece of public data, and then we kind of increased the public data over time, so 5, 10, up to 200 points of data. And what we found is that actually, with as few as 5 data points, we were actually able to completely determine what the electricity generation costs were on the system. So, admittedly, for those who know power systems, a 14-bus test case is actually a relatively small test case. It is far from the scale of a full power system. That said, 5 data points is also far less than what you would have on the power system. In particular, we actually have this data, the public data, hourly over multiple years. So that's a couple tens of thousands of data points. And so these preliminary results seem to indicate that the data that is published right now may expose generator costs on the actual system too. So guessing generator costs was pretty easy, but guessing the grid structure is a bit harder. And to explain that, I'm going to show the results of one experimental run, or 2 experimental runs, one for 2 different parameters, as we progress in our algorithm. So that's the graph shown here. On the x-axis is our quote-unquote public loss, so this distance between our estimates of the public quantities and the real public quantities that I was talking about before. And when the loss is high towards the left of the graph, that's the start of our algorithm. And as we optimize our algorithm, we move rightwards on this graph. So at the rightmost side of this graph is where we've actually stopped our algorithm and said, I think we have the correct guesses for our private parameters. And on the y-axis is a squared error of our guess for the parameters. One parameter is a solid blue line, and the other one is a dashed orange line. And since grid structural parameters are complex quantities, this is actually the real part of the grid structural parameters that you're seeing here, and then we also have a plot for the imaginary part. And the part of the graph that we want to look at is this very right side. So when we stop the algorithm, when our loss over the public quantity is 0, have we actually recovered the private parameter correctly? And here in one case we have. In one case, the loss for that parameter is, the squared error of the private parameter is 0 at the right side of the graph. But for the other one, we haven't. And so we can frame this in terms of identifiability. Basically, some structural parameters are easily identifiable. They do actually determine the outputs of the system, and others don't. So again, these are preliminary results on a 14-bus test case, and we're looking to expand our analysis and make it more robust going forward. So in the last minute, I kind of want to talk about what this analysis means for policy making. So what can policymakers actually do based on the results of our preliminary and eventually final analysis? So the first option they have is actually to stop publishing data. Of course, as a data scientist, that makes me kind of sad. And in particular, I don't necessarily think that's a great idea, in that, as I mentioned before, there are really good reasons that the public data is public for market transparency and environmental objectives. And so there's actually a huge toolkit of options that policymakers can use besides restricting data access to improve the grid based on the results of this analysis. So on the market side, there's the option to, based on knowledge of exactly what data is leaked, to design more robust markets that won't break even if that data is exposed. There are also things we can do outside the market, like pay generators in ways that incentivize them to not game the system. And we can also update our heuristics. So currently, power system operators have heuristics to determine if somebody is actually unfairly operating on the system. And so based on the data we have, we can update these heuristics to actually catch people who might be offending here. On the cybersecurity side, There are actually a couple of things we can do as well. So for instance, Idaho National Lab has a power grid test bed that is used for a variety of things, data mining, cybersecurity analysis for the power system. And so one could potentially give civic hackers the outputs of our analysis, say, you know these grid structural parameters. What parts of the system can you actually break based on that? And then, based on the results that the civic hackers are able to obtain, we can actually design measures and policies to fix that. And then, of course, we can also use formal system verification methods, so actually go do the mathematics of the system to see what breaks or doesn't break based on the information available. So to summarize, in this talk, we proposed a method for assessing power grid data vulnerability by reverse engineering the AC optimal power flow problem. And what we want to say is that policymakers have a variety of options that they can use in order to use the results of this analysis to make the grid more robust. And with that, I'd like to say thanks. Thank you so much to the organizers of this workshop. And if we have time for questions, thanks.
Thank you. Any questions? So I have one. Okay. There's a movement now to decentralize and distribute the actual generation to go to like rooftop or smaller solar panel yards. How does this still pose a threat, or does this prevent the threat, or is are these issues still present?
Yeah, I think to be determined. I think these issues would definitely still be present, even in the presence of rooftop solar. So one kind of wrinkle that comes along with rooftop solar is that solar panels input power into a part of the grid called the distribution grid. That's the part of the grid that's the closest to consumers. And historically, we don't actually have a bunch of sensors on that system because we didn't expect to have a two-way flow of power there. And as a result, in some sense, I would argue that there's a little more room for fudging or weird behavior, because if power system operators don't know what's going on in that part of the system, then they don't necessarily know what's going wrong on that part of the system if someone is gaming. On the other hand, of course, if these solar panels are not bidding into the market, then all of a sudden we have a larger pool of power that's no longer on the market, and so as a result, the influence of the market and the kind of effect of gaming on the market is much less widespread. So I'd say the jury is for sure out on whether distributed solar, for example, will help or hurt in this case. Yeah.
Oh, some more questions?
This method works because you know what optimization algorithm the power companies are using. If the companies chose to stay slightly suboptimal and did that in a random manner, would it still work?
So so the question you asked is if they did, and actually the answer to that is they currently do use suboptimal algorithms to schedule the power system. And so
no, I didn't mean suboptimal algorithms.
Mm-hmm.
Known algorithm, but stay on an epsilon suboptimality set.
I see. No, so I mean, I guess what I'm saying is they could do that, or they currently use known algorithms, but different algorithms that are actually worse for the system. So I think the question you're asking, if I'm understanding correctly, is are we actually using the correct model here to model what the power system is, the power operators are actually doing to model the system? And so I guess there's a twofold answer to that. There is one.
No, I'm asking how sharp is the optimal set?
Right. And so I guess what I'm saying is there's one possibility that the AC optimal power flow algorithm is brittle enough that we would then not be able to actually ever get to zero public loss on the system. But on the other hand, if we are able to, and I think the jury's out on that, if we are able to, then even though the power system operators are using a different algorithm than we are, at that point, if you're able to basically describe how the system is working, then you can still fudge with it. So, yeah, thanks.
Is there one more over there? Was there one more question, or? Okay.
Okay, thanks so much.
Thank you.